Microchips the size of a grain of sand now have a revolutionary capability: flight. A team of engineers at the Northwestern University near Chicago, headed by the bioelectronics pioneer John Rogers, has developed a winged microchip with a wide diversity of applications in pollution monitoring, disease tracking, population surveillance, and perhaps even space. The microchips, now being called microfliers, have been inspired by nature, in particular the way trees, such as maple trees, used winged seeds that glide through air currents to spread tree populations. The microflier designed by Professor Rogers and his team are bioresorable, or electronics that can harmlessly dissolve in water in order not to create electronic pollution or waste. The microflier is the smallest ever human made structures that can be dropped in the air by tens of thousands or even more, depending on the use it is being put to gather data and electronically transmitted to a centralized database. This is science fiction becoming science fact in front of our eyes. Professor John Rogers, who has a PhD in physical chemistry from the Massachusetts Institute of Technology, spoke to Mayank Chaya Reports. On a separate note, we apologize for the slight echo in the audio. Your microflier is essentially a very tiny chip which has been given the ability to use air currents. Is that something that I understand it right?
Yeah, that's the key novelty, of the concept and what we're, focusing on in this initial publication. My research group has been interested probably over the last 15 years or so in the development of very tiny devices that integrate with the human body for monitoring various health processes.
Right.
And we identified an opportunity to adapt those classes of devices for use in environmental monitoring. But the challenge there is in wide scale dispersal. How do you get these tiny devices spread out across the environment, across the atmosphere, for providing that kind of monitoring functionality? And this kind of passive approach to flight is our idea for how to do that.
How is the area of coverage determined?
Well, it's determined by the design of the device, the size of it, the mass, essentially the flight properties. But it also relies on wind current, naturally occurring patterns of airflow. And the devices are really designed to maximize the time of engagement between the device and those patterns of airflow as the device is falling to the ground. So you imagine launching them at some altitude with a drone or maybe an airplane or other means, and then they float in a very controlled way through kind of a helicopter motion down through the air. And during that flight, they can engage with the wind to affect that kind of dispersal, very much in the same conceptual way that plants disperse their seeds. Trees and various types of plant life take advantage of that type of concept, and we're leveraging the same idea.
That prompts me to ask you whether these microfliers are biodegradable. What happens once their use is over? Because it must be in large quantities that you spread them, right?
That's what we're envisioning. So that's a great question. And I think if we didn't have a good answer in mind for that question, we probably would not have started down this path of engineering development, because I think electronic waste and pollution and litter that could otherwise be associated with devices of this type that are not biodegradable would be a serious drawback, maybe a showstopper in terms of consideration.
Right.
So we are leveraging materials and device designs, manufacturing concepts that we've been developing over the last decade for bioresorbable temporary implants. So electronic devices that are similar to a resorbable suture, but which support all kinds of electronic functionality in biosensing, wireless radio communication, power supply, and so on. And so we can take that technology foundation, originally developed for implants for the human body, and use them in these kinds of environmental monitors so that they just naturally disappear, resorb, dissolve away into the groundwater to environmentally benign end products. And so we know how to do all of that. We demonstrated a simple example of that kind of environmentally resorbable flyer device in this first paper. But that's very much a central focus of our research going forward, is to develop and demonstrate those kinds of capabilities in digital sensing devices that are environmentally compatible, degradable.
This is extraordinary. People don't realize this is actually science fiction unfolding in a sense. Tell me a bit about the genesis of it. How did it occur to you and your team to do something like this?
Well, I guess a couple answers to that question. We just talked about bioresorbable electronics, and there's sort of a certain origin for that concept, and then the development pathway, and then there's kind of a separate point at which we launched this work on very tiny flight structures. They're separate in their origins, but they've come together in a very synergistic way, as we just talked about. So for the bioresorbable electronics, it originally started through research funded by the Department of Defense. They were very interested in electronics, sophisticated classes of electronics that could be deployed, in remote areas without suffering risks associated with recovery by an adversary. So the idea is a transient, physically transient form of electronics that could disappear over time to eliminate the possibility of that technology diffusing out to an adversary in an uncontrolled way. So that was really the origin. We got a little bit more interested in that concept in the context of temporary devices implanted into the body that could monitor a wound healing process, for example, and then disappear after the wound is healed. The device is no longer needed, so it would kind of go away in a natural process dictated by the materials. But now we're kind of coming back to the idea of deploying these same types of platforms in the environment, but not in the context of a military application, in the context of environmental monitoring. So it's kind of funny how these things go through twists and turns, and you follow opportunities, and it evolves over time. But we've been working in the space for a long time, for the resorbable devices. And so that's kind of the summary story of how that research thread developed over time. And then the flyers, much, much more recent, probably started that project 3 years ago. And motivated, in the way that I described. We're doing a lot of things on the human body. Hey, why can't we leverage those same technologies for environmental monitoring? A lot of applications there. How do you disperse them? Thinking about how biology does that. Started with the idea of creating an artificial insect that would fly around, but that's really tough to do. So we looked at the plant world and thought about maple seeds and distillation seeds and dandelion seeds, and how are they doing it? And how did evolution sort of arrive at those solutions? And could we take inspiration from that and then engineer flight to address our requirements? A little bit different than seeds, but it's interesting how these different things come together, and this is turning out to be a pretty amusing direction for research, where we think there could be some real impact.
Right. You mentioned maple seeds, helicopter seeds, as it were, which are a single-winged seed, right? How did you think? Connected to that is the question of trajectory. Your microfliers are very well controlled in terms of determining the trajectory, in contrast to maple seeds, which just go to random places because that's part of nature's evolution. How did you manage to get the trajectory so precise and something so tiny?
Yeah, that's a great question. So a lot of this first publication is around establishing the fundamental physics understanding of how tiny structures interact with air during free fall, and during random air currents that occur naturally in the environment. And we got very deep into those details. We understand in a very fundamental level how maple seeds work and they do actually a pretty good job. If you take a look at them, I mean, they spin pretty effectively if you think about it, and that's a design that evolution has landed on, through hundreds of millions of years of evolutionary processes. But for us, the design constraints were not nearly so severe. And so we could begin to look to more sophisticated layouts in terms of the numbers of wings and the attack angle and the geometry and so on. And we're able to explore structures that have much smaller dimensions as well, because we don't need to carry the full complement of nutrients and genetic material associated with the seed. We're talking about really tiny microchips, and so it's a different set of considerations, but I would say just purely defined by metrics like how slowly these structures can fall as a result of that helicopter motion, and how deterministic is their fall trajectory. What is the stability of that falling motion? We do quite a bit better than biology. That's not to say really that we've beaten nature in any sense, because nature is optimizing across many other parameters. They have a much tougher problem to solve than we do. But by those two metrics and by the overall dimensions of our devices, we're like way better than what you would see in seeds
Right.
for our purposes.
How much does the one chip gather in terms of information? And related to that, is there a transmitter that sends out that information?
Yeah, so there are variety of ways you can use these, flying structures. The simplest way is to take the structure and then just coat it with a thin film of a chemical material that changes in color depending on the concentration of a species of interest in the environment. So you can measure pH, for example, using a color changing chemistry, one that's derived from plants, actually. So back to this idea of environmental compatibility, really kind of focus on that. The other kinds of color changing chemistries that we've demonstrated respond to heavy metals in the environment: lead, cadmium, and mercury. So that's the simplest way. So then you have very low cost passive structures. They're flying in a passive mode. They're sensing in a passive way defined by the chemistry. And then the wireless readout happens through high resolution digital photography captured with a drone. And then you do color extraction and you can determine then the spatial pattern of concentrations of these species. That's the easiest thing that you can do. It's the lowest cost approach to environmental sensing. We like it a lot. There are limitations, though. So back to your question, we have designed these structures and the manufacturing schemes that we use to form them to be completely aligned with the manufacturing schemes used by the semiconductor industry, the kinds of schemes that are used to form integrated circuits. So there's a natural synergy there. So we can incorporate, in principle, any type of digital integrated circuit and semiconductor sensor onto these platforms. We can really do anything in that sense. Then the question is, what can you do economically? What can you do in very small dimensions? How are you going to deliver power, and how are you going to do data communication? And so there's a lot of different options there. We have demonstrated in this first paper a simple one where we're actually measuring solar light exposure as a structure is falling to the earth. And then once it lands on the ground, it transmits that information digitally through a wireless connection.
I see. You know, are you in a position to tell me at what height these might be dropped from?
Could be anything,
Oh, I see.
any height. I mean, it would depend on the application, obviously. We did develop theoretical models that allow us to understand how the flight dynamics changes with altitude. If you go very high, the density of air is much lower. The aerodynamics are quite a bit different, but we understand all of that. So in principle, any height, and you would just need to think about the application requirements, and then the changes in the flight dynamics as you move from very high altitude down to the surface of the earth.
And logistically, if I'm, say, for instance, a client buying these microflyers, how am I getting a certain number? How do you pack them? I mean, these are minor details, but I'm interested to know how you're going to ship them if somebody wants it.
Yeah, these are great questions. I mean, I run an academic lab here at a university, Northwestern,
Right.
and we're really kind of focused on new concepts, new schemes, engineering ideas, and foundational physics, chemistry, materials, that kind of thing. That's kind of where we are in the development of
Okay.
this technology right now. We are very interested in ideas that can be translated out of an academic laboratory into the real world. So we definitely think about those kinds of things. And one of the reasons why we developed a manufacturing approach is aligned with what's done in the semiconductor industry today. Because if you don't have that alignment, then you're really highly constrained in what you can do, and the costs become potentially unmanageable. So we definitely think about those kinds of things, but maybe not to the level of granularity that you're asking, in terms of like how you would package them up and things like that. Great questions, but this is the very first paper on this type of concept. We're still in the early phases of kind of working out some of the details, but we're hopeful that we will have answers to those questions and we'll be able to think through those issues over time.
What kind of timeline are you looking at in terms of commercial availability of these flyers?
Well, if you think about, the digital, so the colorimetric ones, would be ready to go on a very near term
Okay.
timeline. I think we would look to partners to do the commercialization and the deployment. It's not the core of what we do as an academic laboratory. We don't have manufacturing facilities. We'd love to have conversations with people who are interested, have specific applications in mind. I think that could happen very quickly. For the integrated circuit microchip type flyers, I think we would be able to leverage the commodity RFID tag type devices that are in widespread use already. So the kinds of ways that those tiny chips are fabricated and packaged, I think there are great synergies there. And so we'd be thinking of costs in the range of 10 to 20 cents per device is kind of what we're thinking about, maybe lower. If you think about the technology trends in the semiconductor industry, it's all about making things smaller, lower in cost, more powerful. So there's a great development trajectory there that we'll be able to leverage over time. But right now, I think the most closely related device that exists in the commercial world is an RFID tag. When you take that technology, you merge it with a flyer, you add a sensor, and that would be the path forward.
I still can't get over the fact that this is essentially it's going to just dissolve away into environment. Uh, the central part of your microflyer, namely the integrated circuit, the chip, is that also dissolves in a sense?
Yes, yes. So we've worked all of that out. Like I said, we've
Oh,
been interested in this area for temporary implants for a long time. It's a
right.
decade we've been working on it. So we have papers we published with commercial semiconductor foundries that describe recipes by which you can change a few of the key materials in the silicon integrated circuit. You process it a little bit differently, but in a way that's compatible with the manufacturing line. And the result of that is a microchip that dissolves in water to end products that are not only compatible with biology, with the human body, but also benign to
Right.
the environment. So we know how to do that. It wasn't the focus of this paper because we already figured that out, but we can kind of take that knowledge, combine it with the flyers, and achieve this kind of environmentally resorbable
Right.
device.
Given the high end of your work, is this technology going to be controlled in terms of who it is available to?
Yeah, I mean, as an academic group, we put pretty much everything in the public domain, and
Right.
so the advantage of that is there are no secrets. Everybody can see what we're doing. We're very open. I think that's an important part of the how the scientific community works and how advances are made over time. Small companies don't operate in that way. Big companies also don't. All kinds of proprietary secrets and things like that, and you sometimes don't know what's going on. The disadvantage of being open is, as you are suggesting, anybody can go off and do it. I mean, it's not easy. You have to have the right facilities. You have to kind of know what you're doing, but it's there. You can read
Right.
every last detail in the paper.
Oh,
So
that's yeah.
um, Yeah, that's just a consequence of how we operate in an academic setting.
I'll wrap it up soon. I'm reminded of an episode from The Big Bang Theory where the DoD or the Pentagon steps in. do, do you see something like that happening to your technology?
I guess for defense, if it's really defense purposes, I'm fine with that. I mean, if it's a defensive mechanism, I guess I don't see these devices being used in kind of an offensive mode, right? So I wouldn't have a problem with it. I mean, we've received and been, fortunate to have support from DARPA and Department of Defense over the years, various different projects, and if we can help defend the nation, then that could be a worthwhile thing to work on.
Right. It strikes me even as I'm talking to you that this possibly has space-related application in terms of, for instance, say in the clouds of Venus, there was speculation that there is
Uh,
microbial life, right?
that's a
In
great suggestion. I hadn't actually thought about that interplanetary monitoring. Kind of
I
focus on,
thought of it the moment I read the story.
yeah,
I said this could end up on Mars or on Venus. That was my
great.
first
Yeah,
instant reaction to it.
that's amazing. Yeah, that's a really creative thought. I mean, I guess small size, lightweight, it's the kind of thing you could put in a payload on a rocket, without.
Absolutely.
Yeah, yeah, yeah.
Maybe
We're
you
kind of
should reach
focused on
out
the
to
Earth.
NASA or Elon Musk, one of the two, preferably
Yeah,
NASA.
yeah. Great idea.
Yeah.
Appreciate it.
Just to wrap it up, I know this is not a question that you grapple with, but at some point there will be a question about how its availability is controlled. Because if it falls in nasty hands, it could be misused, right?
I suppose you could say that about any new technology. I appreciate it.
Right.
I think it's important to consider that. Um, Nefarious uses of any kind of new technology. Um, we'd be happy to work with others who are in a better position to understand how to control the dissemination. But yeah, it's not our core expertise. But we'd be happy to work with authorities as necessary. But I don't see an imminent threat here. It's not a weapon, at least it's currently configured. So.
And finally, have you visualized the size of the swarm in order to say take a sample of if you're tracking a disease or if you're tracking animal population, if you're tracking something else? Do you have any size in mind on how many of these chips might be needed? I know you said it depends on the application.
Yeah, I guess we're thinking about scales of thousands, I guess,
I
where
see.
each device is maybe a millimeter in diameter. Kind of that scale and scope is kind of what we're envisioning. But as you mentioned, the application would dictate the numbers, the area coverage, and maybe the size of the individual devices. We can build them any size you want. We can go much smaller than the structures we've reported. The problem is that once you drop below a first certain dimension, they stop flying. Everything looks like a sphere, it just drops right down. So we've gone to the smallest possible dimension where you still get this systematic helicopter motion, but we can go to much larger sizes. So it's
Yes.
pretty versatile in that sense.
I suppose if you make it even smaller, it may just not even land, right? It will just
Yeah,
stay in the
yeah,
air.
right, exactly. Yeah.